So, and I'm very happy that Andreas gave me 10 additional minutes because I have no idea how to fit everything in that time that I have. And so perhaps everything will be a little bit squeezed. Could we switch to my computer, if possible? Yes, that's the right one. Okay, you see a lot of white space. Okay, let's start like that. Alice was beginning to get a little tired of sitting by her sister on the bank, of having nothing to do. Once or twice she had peeped into the book her sister was reading, but it had no pictures or conversations in it. And what is the use of a book, thought Alice, without pictures and conversations? So, yes. And what is the use of a book, thought Alice, without pictures and conversations? And I think that's why we are here, because we are providing the pictures, the conversation, everything that adds to the text, in a sense. And so we are all somehow Alice, getting bored by only reading and trying to do something, to create something. And I today want to give a talk on fast prototyping of interactive mathematical content. And well, I first have to explain you what I mean with that talk. So let's look at the different words. Let's start with interactive. So interactive for me is everything that really gets people involved. So you have a kind of exhibit, and the exhibit is not only something to look at, but also to do something and to experience, to learn, to become active in a way. Content. I today will mainly talk about virtual content. So things that run on computers, things that run on apps, but many of the things I'm telling you today will, not literally, but on a kind of meta level, also apply to physical exhibits. So I will really talk a lot about this prototyping phase here. And well, I think it's a good idea to have a clear knowledge what shapes an exhibit when you start to plan it. And I think it may also be relevant for some parts of the workshops. Okay, other thing, fast as possible. So things have some natural boundaries. So if you want to make something really complicated, it needs its time. But at least we should get rid of everything that is superfluous in this building process. That things is, we in programming always call it the boilerplate code. So you're doing a program, and there are some parts of the code that you have to do every time you start a new project. And if you do them every time, so you don't have to do them at all if you automatize that process. And I'm talking a lot about not talking about boilerplate code. Prototyping, well, by prototyping I really mean the first stages of the design that in a sense very often shape your project. And these proof of concept implementations which will somehow form facts in a way. And I must admit that doing something in a final form very often needs time, and making something final and accessible will more or less always, well, you can put any time you want in that process. But in the first part of the project, it very often pays off to be fast. So I'm mainly talking about kind of public scenario where you're talking about exhibitions, about apps, about school books. So you should think of contexts like, for instance, this here, where you have, this here is in the German Museum, this is in my own math exhibit, this is a school class, so where people really get into interaction with it. So, Andreas said that I'm involved for some time already in imaginary, and I will have to tell you something about personal history. But before that, so what I'm talking about is in a sense design history, design philosophy on the one hand, and on the other hand, I'm talking about authoring tools. And actually what I want to talk about is authoring tools which incorporate already some design philosophy. So where the tool is built in a way such that you, by definition, are fast in the first stages. Okay, now for the history, because this year somehow for me is a little bit special. So that's perhaps the most personal part of the talk. So I started my first project involved to public exhibitions 30 years ago, and almost, well, it was spring, somehow 1968. I was a student at Darmstadt, and in Darmstadt there was this famous symmetry exhibition, and at that time we programmed something on the Atari. The Atari is a prehistoric computer. I know. And this was really very innovative, what we did there. Then I had to study for some time, doing a PhD, and at a certain point, so in my PhD, I developed methods for automatic proving in geometry, and for that prover, I wanted to have a kind of input interface where you just can draw your geometric theorems, and there I started another project which is called Cinderella. So Cinderella is a kind of dynamic geometry program, at least it started as that. Now it's a kind of very general tool for mathematics visualization. And you see, well, this project now is about, well, 24 years old already. Then there are some other things, and let me just divide the upper part here for tools and the lower part for content. And then I, in 2001, got this chair in Munich, and there I opened a small mass exhibition, the X Quadrat. So X Quadrat is really more or less literally describing the exhibition, because it is a room with 9 times 9 meters. And if you read this IX here as a Roman number, so it's 9 times 9, and close to the X Quadrat we had the first appearance of imaginary, so this is a place where people really interact. And well, at some point, imaginary came into it, and Mathe Vital, which is an internet portal. I collaborated, for instance, with the Deutsche Museum, and at some point I started other projects you will hear about. For instance, I started to write apps which are somehow related to that point. So here you see some loose connections about symmetry drawing, and just recently we started a new project which is now really a crucial part of what we are doing, which is kind of follow-up for Cinderella. I will explain what's going on there. So it's called Cindy.js. JS stands for JavaScript because, well, Cinderella was written in Java, or is written in Java, and most of you will know Java in the web simply died, and at some point we had to think about alternatives. So talking about fast prototyping, I want to focus on, well, a tiny part of this time scale, approximately here. So that's the time between 26 November of 2015 and 17th February of 2016. And Andreas is already laughing. Because if you are working together with Andreas, you have to be prepared for fast prototyping. There is no other way, because things like that happens. He gives you a call at November 2015, says, well, there might be this cool exhibition in Heidelberg, and we will do something really innovative there. I don't know whether this will really actually happen. But it's very likely, And so would you contribute? Just wait. Okay, so then you just wait, and on January 6th, you get an email from him. Okay, let's go for it, I got the money. And then you ask, okay, it was somehow spring or summer or so. No, it's February. So actually, this is Andreas, Christian, and me. So it's really a cool project between two big discounter supermarkets in a shopping mall. And actually, This was 17th at 4 a.m. in the morning, though we were still sitting there, and already at 3 p.m. in the afternoon, people were really actively using that. And this is an exhibit that really runs 7/24. So this is really designed for very stable use over a long period and continuous use. So, what I want to do today, and I hope I haven't used up too much of my time, okay, that's still good. I want to give you 5 software demos. 5 demos of different projects that are more or less interconnected and have their interrelations. And from each of these demos, I want to draw out some lessons to be learned. So I already told you that I work a lot with Cinderella, so that's our own tool. And first of all, I have to introduce you to Cinderella. So the first demo will be about Cinderella. And the lessons to be learned is, well, first of all, I want to introduce the tool. And the second lesson is what I just said, avoid boilerplate code. So what is Cinderella about? So Cinderella is a program for doing dynamic geometry, and this here is some screenshots where Cinderella just does some really geometric parts. But in the meantime, Cinderella grew over the years. So there was a time where people asked for more and more functionality, and at some point we really decided to seriously enlarge the scope of the program. So Cinderella is a joint project of me and Ulrich Kortenkamp, who is a professor at University of Potsdam. And so the current architecture of Cinderella looks approximately as follows. Well, there is like a kind of, the very, very old part of the cortex. There you have the geometry part. But on top of that, you have a scripting language which is very high level and versatile, and you also have a physics simulation engine. And putting these 3 things together with very thin interfaces between each other, you can do very interesting things. And so the main philosophy behind Cinderella is it should not be a specialized tool. It should be as generic as possible within its scope. So you cannot cook coffee with it. And you cannot directly, create videos from it. Actually, there was some time where we had a subversion which was called Scenerella, where you could create videos, but that process at some time was no longer followed up. It should have no artifacts. So if you do a program, and this program should model mathematics, then this program has some inner logic. And the logic behind Cinderella, we try to have it as close to mathematics as possible. And actually, this is really complicated. So at that part, really serious mathematics is involved. It should be modular. You already saw that in the global design. I would say it should even be atomic. So there should be very, very small units that work together in a good way. Think of it as a collection of Lego bricks, in a way. And it should be easy to use, but at the same time, it could not be oversimplified. So think of Einstein, who said things should be as simple as possible, but not simpler. So if you want to cover a certain range of problems, you must essentially also have a certain complexity. So let me start with a demo, and this will be a challenge with this microphone here, but we will make that somehow. So perhaps at some point I have to switch to some other mode of talking. Okay, this is Cinderella, and I don't want to talk a lot about the geometry part. I want right away talk about things where different parts come together, but I still want to show you at least a tiny example what you could do just with geometry. So what you see here is a circle with a center, and here's another circle with a certain center and a fixed radius. Let's take the third one with a point that is related to the boundary here. And then let's just add a few line segments. So this is a quite simple construction. So the good thing, I don't move it at the moment. So did you recognize what I just constructed? I made segments whose lengths are dependent on the radii of circle. So if I don't change the radii, the lengths won't change. And if I start to move that, it behaves like a little mechanism here. And so this is not physics, this is just mechanism, just geometry. And for instance, you could ask, well, if I take this middle point here, what is the trace of that middle point? And you see, well, this is a trace, and this trace can have, in fact, very interesting shapes. So if I move around the thing, so you see, everything can happen here. So not everything, but in its scope. So let's make this here a little bit bigger. So you see this has really interesting stages, and if you don't believe that this is the right thing, you could say, well, please animate that for me, and you see that this is really the right curve. The reason why I'm showing that example at the very, very beginning is if you want to do that right, you really have to dive into mathematics. And if what Cinderella in the background does, it makes complex detours, so it embeds everything in a complex ambient space. It resolves singularities by making complex detours, and I could give one-term lecture about what you see happening in that picture. I won't give that. It would be fun. I want to do something very different and jump to the other end and show you what you can do if you combine physics, scripting, and a little bit of geometry. So geometry will be almost invisible in this example. So let's first draw a box. So this here is a box, and in that box let's put some, oops, I have a little problem. No, I don't have a problem, just other configuration. So these are masses. So if you have a mass, it may move. So if I press this button, you see nothing happens because there are no forces involved. But you could, for instance, pick one of those points and say, okay, go ahead, and well, this one point will have a life. So far, not very interesting. But you could say, well, let's take all these masses and let's charge them. So select all these things and say, well, each of them should have a charge, and let's assume that charges really cause forces, and if you then press the button, something like that happens. So the parts repel each other, and you see a little small particle system. Now I want to show you how, with very, very simple and basic ideas, you can go from there to a little swarm simulation where these particles become models for fish, essentially, that follow up in a swarm. So you see, so far, we did almost nothing. No boilerplate to create that. So let's open the script editor. And now I have the problem that I will type with one hand, but I'll make that. That should be doable. No, let's do it like that. I think that works. Oops. It's also physics simulation. Okay. So let's do something with that. And so the scripting language, think of it as something like Mathematica, but only doing number crunching. So take Mathematica, throw away the symbolic part, and just do the number crunching part of it, and then you are close to our scripting language. So there is, for instance, a statement that is called all masses. Oops. That's exciting. So that is called all masses, which simply gives you a list of all involved masses here, and let's call a variable masses to be all masses. And first of all, let's find out how many of them are there. Let's say n is the length of this list. And as a first thing, let's say, calculate the average position of our particles. So what would be the average position? So you sum up over all masses, and let's call each mass m, and you sum up the x and y position, and you average by dividing by n, and you draw this thing. Let's call it mid. Draw mid. So I added a little script now, and if I start that, you see a little green point here, and this little green point is directly coupled to the animation. Though if I start it, you see, by the way, it's already interesting mathematics that this green point moves significantly slower than all the other points individually. So let's continue and say, well, if this is a swarm, so what is the basic idea of a swarm? A swarm would be, well, I see some fish and I want to be where they are. So let's just correct, so how do I get there? I have to correct my velocity in direction of the others. And so I could say, well, for all masses, or let's do it this way, I go through all masses, and for each of these masses, I correct the velocity, so I can exit the velocity by this dot v, and I want to say, well, it is my old velocity, but I want to add a little bit a component of, well, where do I want to go? I want to go to mid, so I need the difference vector of where I am to mid, and I want to add this to mass. And if I do that, you see it gets wilder and wilder because things heat up in a way. So we have to, so fish cannot swim that fast. So let's restrict the velocity by saying, well, let's take m, let's take the velocity and say it is the old velocity divided by the absolute value of the velocity. So now everything has a normed velocity. Perhaps let's make it even a little bit slower, something like that. That's too slow. So, okay, you see playing with the parameters is an interesting thing, and you could perhaps put that on a slider. And so we are close to getting an exhibit here. I don't know whether you recognize it. We're just creating an exhibit within 5 minutes on the fly. So these are not fish, these are mosquitoes, more or less. So mosquitoes don't sense the speed of their neighbors, so let's sense the speed as well. So let's say we don't only have a midpoint, we also have a mid-velocity. And we again correct the speed in direction of, well, let's swim like the others do. It's political. This was a joke. So, and with this correction, you see they move coherently into one direction, and let's make it just a little bit more optically interesting and say, well, each of them should leave a trace, and perhaps not too long, and the trace should dim out a little, and perhaps we don't want to have labels on it, and we created quite a realistic swarm simulation just by doing almost nothing. So we essentially had 9 lines of code, where one of them was a drawing, which doesn't really count. You can teach that to people. You can really explain other people how to do these things. So we actually do that. One important thing, so you could also say, please export that to an HTML page. And then we got an HTML page, wait a second, this one. Here you go. Now this is running on an HTML page and you can put it on the web somewhere. And so let me come back to the talk. And so this was essentially part of a workshop that we did about complex behavior from simple rules, where we talked about two things, namely crystal formation on the one hand and swarm formation on the other hand. And we taught teachers how to do that. And these were the teachers sitting in our workshop. And I really was amazed. They got the fun, so they got into a level where they could do these things completely on their own within, I would say, 2 or 3 hours from scratch. None of them experienced in programming. And these teachers then went to their classes, and so I had contact with one of them, and they said, we had this battle in our class. We wanted to find out what is better, a little robot that cuts the grass or a herd of sheep. And so they simulated on the one hand a robot and on the other hand a herd of sheep, and found out that the herd of sheep was much more effective if it doesn't forget some part of the grass. So if it gets disconnected from one part of the grass, it won't get there back again, except for accident. You could also, I should show that to you, wait a second, I have to show you one thing. You could also do these things more realistic. So I have to open a website. This is somehow our showcase site. And on that showcase site, okay, the net is a little bit slow here. You have, for instance, this here. So this here is now really the playground where you really can say, I want them not to care about position and not to care about direction. I want to let them to care only about position or only about direction. I want them, for instance, to see only one neighbor, which is interesting, which has to do something with molecules. Let's see, just two. So let's take away the direction. So you see little molecules are forming here. So you can really learn a lot from just these simple things. It's also interesting to find each other and a third one chases them. That's a well-known party game among teenagers. So you see, you can go further here. Okay, I have to speed up a little, otherwise I will go over time. So what we are trying to do with the Cinderella project, we want to try to give a very natural, high-level operations that avoid everything that should have been done always over and over again. And so here is a little list of the scope of what we're doing. So I don't go into every detail, just want to mention one part here. So currently we are working on an interface that allows our scripting language to run directly on the GPU, which gives a high-level access to parallelized graphics power, which is fascinating. Okay, demo 2, I talked about the German Museum, and the lesson to be learned is now something about interface design. And the main lesson is, if you create an exhibit, try to focus on one phenomenon. Don't put everything into one thing. And so this here is the Deutsche Museum in Munich, and they have a little part in the museum where they show mathematics, and together with Andreas and another group of persons, we created this interactive part where, here you see server, here you see J-Reality, and here you see Cinderella. And I want to talk a little bit about the Cinderella part. So what we did there is we provided a grid of, single phenomena that we wanted to show. And each of them really focuses on one effect, but you have a rather big range of different effects that you can see here. So the typical design cycle of such a single part in that grid looks as follows. You have a prototyping phase that should be rather short, where you fix, I want to show that, and the basic functionality is that, and then you start to polish. And I think there's no way of omitting that phase, but this part here is really a crucial one. So I would say, as a basic guideline, think as simple as possible and think about what you really want to show. Focus on one effect and try to minimize the user interface. And these things can really also literally be taken to physical exhibits, not only to programming things. And here are a few screenshots from our things from the Deutsche Museum. So you see, for instance, something about moving mirrors and about kaleidoscopes and about Archimedean solids or Sierpinski tetrahedra or a program with which you could draw ornaments. And I just want to, I didn't know whether I will do that or not, and I will do it. So here is part of the grid, just that you get an impression. So here you have, for instance, some spirals, and you can move your Gartenzwerg, or just another one. Let's take this one here. Here you have platonic solids, and you can see how does an octahedron fit into a cube, or how does an icosahedron fit into an octahedron. It's amazing. If you divide the segments in the golden ratio in the octahedron, you get an icosahedron, and you can play with that, and I think you get the idea. And having this in a shaped form, and actually I have to admit shaping took some time here. Okay, the fish are still running. Shaping took some time here, was a complicated process, but the prototype phase for each of these things was rather simple. And right after the opening of this exhibition, I did something which is almost nothing, but which was perhaps one of the most important things I did over the last 10 years. I took screenshots of what we had there and put them on my iPad. We are now 2011, iPads just appeared on the market, and I sat together with an editor from an online company providing interactive content, and I showed that to him, and he immediately went into that images and wanted to do something, and nothing happened because this was just a screenshot. And we said, we want to have that on the iPad. And the bad thing at that time was we didn't have any environment that would make it possible to put these things on the iPad. So he said, I will hire programmers who do that. And I said, that's impossible. They need to know a lot of mathematics to do that right. And so at the end, we decided not to do anything, but another challenge somehow started. I wanted to do at least one of those things really good. And this is where some other projects started, this ornament drawing app, iOrnament, which is somehow related to this very, very first activity in 1986. And, well, talking about iOrnament, lesson to be learned, you really want to make it simple, you really want to make it fun, and this is terribly hard. So actually, in that situation, actually the prototyping phase was actually tiny compared to all the rest, but this tiny part here was only due to my experience, not to the working environment. So I had to learn OpenGL from scratch at that time, so I learned a lot in that phase, and it took, I think, over 7 months or so to finish the project, to bring it to something. And I want to show you at least a little of that, how things look if they are polished. So here we are on my iPad. This here is iOrnament, and in its current version you can, well, it just asks you, please draw here. And okay, if I put down my finger and I draw here, so it immediately draws symmetric pattern. I can switch colors. I can zoom in with a very, very high zoom factor, so I can make really small annotations here, something like that. There is even something like a glow pen with which I can only add color, which gives such a nice glowing effect here. So it's easy to create symmetric patterns with that. You can switch between the different crystallographic groups. You can say, please show me what you've done, what I've done in a different group. For instance, in the simplest of all groups, it looks pretty boring. So this is not politically correct. This here is a bit better. You can even go to a situation where you say, please show me what I've done on a sphere and interpret that in a different way. So really, there's also a mass education part in that app. So there really went a lot of design into that app. And noch 5 Minuten, okay, we get that. So I speed up a little. Here comes a little interlude. I spoke about the Java crisis. And the Java crisis essentially is, well, the origin of what we call Cindy.js. So Cindy.js is the JavaScript version of what Cinderella can do. And the lesson to be learned is sometimes you surprise yourself. This happened in that case. I tell you why. So what happened here is, so we had Cinderella as the authoring tool, and now we have this Cindy.js based on JavaScript as a content viewer. Between that, there was this Java crisis where at some point we really recognized we have to redo everything to stay alive. And the point why this surprised ourselves, because now we are about 2014. And I told you that we didn't have a way to put our examples on the iPad. Actually, with this viewer, you can run JavaScript on the iPad. You could have what we had in the Deutsche Museum before. We could just have it on the iPad and say, well, here we have one part of the grid, for instance, some kind of double pendulum, and this now runs perfectly here on my iPad. And we had to do nothing for it, because simply the environments fitted together, and we were so proud about that. So I will make that within the 5 minutes, 3 minutes. So here comes the next demo, which it's about Cindy.js and music. And the only reason I want to show it to you is there's no lesson, it's just fun. So right for that workshop, I started to reanimate the sound interface of Cinderella, and I just want to show you just one demo to see what is possible in principle. So here you have a little rhythm machine where, well, go to your drum whenever you, let's make it simple, or let's make it even simpler. This is very simple. So interesting riffs have a lot to do with steps when you draw lines, and this here is, for instance, is really realistic in the sense that these kind of rhythms appear all over the world. And I just wanted to show you that this is possible. Silence. Almost done. One last demo. Taking everything together. Take iOrnament, take Cinderella, take the new JS viewer, and create something new. As Andrea said, connect everything. And one project we're just working on is the following. So within our page, I have this sub-page here where it tells you, please drag and drop an ornament to that. So you imagine you created a tile with iOrnament, and then you make a drag and drop here, and then you get this here, and you can switch to something else. And if you really want to build it, here's how to cut out your paper. And so you can take iOrnament, create a tile, export it, and use it as a, well, blueprint for creating interesting things. There's also the possibility to create kaleidocycles. So let's take another one. Let's take some, I love my fish. Where are my fish? I'm talking, no, oh, let's take these fish. That's okay as well. These are typical Escher fish. So you can move that here, and you get something like that. And if you want to build it, here is what you have to cut out. And we are now giving with that, so this somehow brings together all different projects, and we are about to start with this in next week. So we already had a little workshop, but next week we will have really the first serious workshop with a full workflow. And this brings together somehow everything I did in the last 30 years in a strange way. And I think I have to thank for your attention.
Thank you, Jürgen. We can have some questions. We have a few minutes left. Where do we have the second microphone? Is it somewhere running around? Or yeah, then you can get it from the back. Jürgen. Okay.
There was a question and the microphone is still... Oh, you can also shout. That's also okay.
Test. Yeah,
oh,
it works.
Cool.
Fantastic.
Test back.
First of all, thank you for a fantastic presentation. That was really inspiring. And my question is about the Cindy.js,
Yes.
The new version. There is a built-in system inside the software for transmitting data in real time, for example, as MIDI or Open Sound Control.
So for the music part, there are two parts for the music. One is directly, so actually the music part is very, very young. It's just 2.5 weeks I started it. So everything is still somehow floating around. So there is one component talking directly to the sound engine where you can provide pure sine functions and doing interesting things with that, talking about really the physics of sound. And the other is I'm just writing a MIDI sequencer essentially. It doesn't, so it uses this JavaScript sound font format where you have little pieces of MP3 which correspond to each node and they are scheduled in the right time. And actually it's really hard because sound is way more critical than optical things. And it's really a hell of programming, but we try to do as good as we can.
Thank you.
There were at least 2 more questions. Some was there, yeah. Yes. It is a complete re-implementation. So if you look at the anatomy of, say, so we had this, wait a second. So these were our fish that we created. And if you look at the source code of this page, it looks as follows. Here, okay, forget about that. Here you load our library. Here we literally have the script that I wrote. So our library makes the browser understand our language, which is a very, very powerful thing because you can still edit in the HTML text. Then it creates a geometry, and actually I'll edit many points at some point. Here are the points. And I said each of them should be a mass. So here you see each of them are masses, and some of the segments were bouncers, and that's it.
And this geometry part is also
part. Pardon?
The geometry part is also
the geometry part is a JSON format that describes the geometry. So you have the part of it which is JSON description of either geometry or physics, and CindyScript that can communicate with that.
So the Java program, when you usually need to add points,
yes.
Could one also just completely manually type everything in and then?
Yes. So actually, I'm currently using the Cinderella engine only very seldomly. I hardcode the HTML, which is much more fun. So may I show one more thing? Just one. Wait a second. I just have to find it because I So I spoke about putting everything to the graphics card. So here you see something that is exported by iOrnament. So it first looks innocent, like, well, just another version of iOrnament. But here you could do deformations with changing parameters. And perhaps if you don't like the colors, you can say, I want to have fancy colors around it. And if you don't like that, you can say, let's make some kind of 3D effect. And what you see here is really at the very moment calculated on the GPU using our language. So the code for doing that is about 20 lines of code. And I know no other environment that has a similar workflow. So,
Is there a reason for the name Cinderella?
yes.
How did you come with that?
The very first plan for the very first version of this thing was done in 1992 in Sweden when I, with Henry Crapo, who is a professor in Paris, was on a boat named Cinderella. And so this name simply got stuck to the project, and I love it. So it's that's the reason. But you could also say it's a computer interactive drawing environment, really elegant. But it was not the reason. One last question? No?
That's it. Oh, thank you.
Thank you so much for the wonderful presentation. Cinderella seems to be an origin, not an imaginary program, but a miracle program. Could you tell me, did you try to think about the reverse problem? I mean, I speak about mechanism, the part of your speech when you spoke about mechanisms. You put some dots, then put some circles, and got resistance. So. And could it be so to vice versa if you are given some trace, some curve? Is it possible to construct a mechanism that be close, not be the exact?
Okay, difficult and deep mathematical question. Point one.
I speak about the theorem of signature.
And,
signature.
So first of all, answering this question somehow really involves deep mathematics. And so we on purpose don't have primitives for these kind of questions because this would not be this generic approach that you should only provide the most fundamental things that you really use over and over in our framework. There are beautiful papers on it. There is a very amazing paper that translates this problem into something of algebra and really creates a literally moving mechanism that even can move a pen with a tilt and everything. I made examples of that with Cinderella, but solving the problem itself is not part of Cinderella. Okay.